All right, welcome ladies and gentlemen. This is video number 3 in our gases unit, so you want to make sure you got your notes turned to that page. And this video is all about the difference between ideal gases and real gases, and under what conditions we can get real gases to behave like ideal gases. So the first thing that I want to remind you of is that ideal gases follow kinetic molecular theory, KMT, kinetic theory. So what does that mean again? Well, we talked a lot about kinetic molecular theory in the first video, but just as a reminder, that means that ideal gases, they take up no space, they have no volume, and their collisions are perfectly elastic, which means that they lose absolutely no energy when they collide with one another. And the reason that they have perfectly elastic collisions is that they have no attraction to themselves, right? No IMFs at all. There aren't any attraction or repulsion between the real gases. These are perfect gases. That's what ideal means. Real gases, however, do not follow these ideas perfectly, because real gases do have volume. They do take up space because they are matter, and all matter occupies some volume. So real gases do have volume. Real gases do have attraction to themselves. So that means that real gases do have IMFs. They are sticky to one another. They have some attraction, and because they are sticky, because they have intermolecular forces of attraction, when they collide with one another, they're going to stick to one another just a little bit, and that's actually going to cause their collision to not be perfectly elastic. That's going to cause their collision to slow down. They're going to lose a little bit of energy in the unsticking of themselves. So ideal gases are perfect, and they follow these ideas perfectly, but real gases don't. There is no gas in existence that has zero volume. That's not possible. So the actual gases that exist, they don't follow kinetic molecular theory perfectly. They follow it pretty darn well, which is why we use it. But you've got to recognize that there's a distinction between this ideal perfection and what actually happens. That's the ideal versus real gases. But the thing is, real gases can actually get very, very close to this perfect behavior. And we're going to talk about real gases getting close to this perfect behavior in terms of size and in terms of conditions. So first up, when are real gases most like ideal gases? In terms of size, smaller gases are more ideal. So we say that smaller gases get a lot closer to this perfect gas behavior than large gases do. And when we talk about size, the easiest way to think about size is think about the gram formula mass. A small gram formula mass versus a large gram formula mass. A gas with a small GFM is going to be more ideal and more follow these perfect conditions than something that's larger. And I think the way that we can think about this is, if you have a small gram formula mass, you're going to have the gas will have a small volume. This is closer to zero. Right? A small volume is closer to a zero volume than a large one is, so it's more ideal. The two most ideal gases that are out there are hydrogen and helium, because H2 has a GFM of 2 grams per mole, and helium has a GFM of 4 grams per mole, and those are very small gram formula masses. So these are our smallest gases. They are most ideal. Large gases are less ideal because they have a larger volume. Carbon dioxide, xenon. Xenon's gram formula mass is something like 131, I think, and carbon dioxide is 44. These are much larger. So they're larger, so they have more volume, so they're farther away from zero. That's not ideal. Ideal gases have zero volume, so larger gases are less ideal than small gases. So in terms of size, our smaller gases behave more perfectly than our larger gases do. And then we can also think about conditions. So under what condition is any gas, large or small, more likely to obey kinetic molecular theory? And the most ideal gas conditions are high temperature and low pressure. So if you have this combination of a very high temperature and a very low pressure, that actually leads to more ideal behavior. The gas is most gas-like under these conditions. Because if it's under high temperature, it's moving very, very quickly. And you always think of gas particles as moving very, very fast. So the higher temperature we're under, our gas is behaving sort of more like a gas. It's moving extremely quickly. And under low pressure, it's going to have fewer collisions. So it has lots of room. It's not encountering the other particles very frequently. Again, an ideal gas, there's a lot of space between the gas particles. That's one of the statements of kinetic molecular theory. So the lower pressure, the more space, that means that basically the farther the gas is going to have to travel before it hits another particle. So it has more space. It's not hitting itself very often. And the way that we can remember this is the acronym PLIGHT. PLIGHT actually tells us everything we need to know, because PL, well, that means pressure is low. And what are we looking for? We're looking for an ideal gas. And then HT, high temperature. So PLIGHT tells us our conditions. Pressure low for an ideal gas and high temperature. So PLIGHT, pressure low, ideal gas, high temperature. Now, this high temp, low pressure thing means that our least ideal conditions are low temperatures and high pressures. So these are the conditions under which a gas will behave least like an ideal gas. And this should make sense because you think about it. Low temperature, it's cold, and high pressure, it's compressed. Right? The gas is very compressed. It's high pressure. It's hitting a lot of other particles very, very frequently. These are conditions where we are getting to be more like a liquid. You're cold and you're compressing it. Well, that's not going to be very gas-like anymore. Now you're starting to turn your gas into a liquid, and that's not ideal at all, right? We want it to be like a gas. We want it to be perfect. So high temperature, low pressure, it's most gas-like. These are our most ideal conditions. And low temperature, high pressure, now you're starting to make it like a liquid. These are not ideal gas conditions. So just two questions that address this. At which set of conditions would gases behave most ideally? Again, high temp, low pressure. PLIGHT. Right? Most ideally. So P-L-I-G-H-T. Just got to remember how to spell the word PLIGHT. High temp, low pressure. In these four choices, we've got a temp and a pressure. So when I see 300, 300, 100, 100 for the temperatures, I'm going to eliminate the low temperature options. I know it can't be 3 or 4 because I want the highest possible temperature. I want 300 Kelvin. And then between choice 1 and 2, now it's down to the pressure option. I want a low pressure, so I'm going to go with choice 2 because 0.5 atmospheres is lower pressure than 5 atmospheres. And then which of the following gases would deviate most from ideal gas behavior? Well, what does that mean? Deviate. Deviate means to differ from. And if it's saying deviate most from ideal gas behavior, it's saying which gas is most different from ideal. Now, when I look at these options, all they've given me are gases. So now I know this is not based on condition. I know this is based on size. So I'm not looking for low temp, high pressure, high temperature, low pressure, because that's not an option. I want to go based on size, and I want to pick the smallest gas. That's most ideal because it has the smallest possible volume, and that's most ideal. So I want to go based on smallest GFM because that's the easiest way to think about size. So looking up the gram formula masses of each of these things on the periodic table, argon is 39.9, neon is 20.2, xenon is 131.2, and helium is 4. We want it to differ most from ideal gas behavior, right? Our smallest gas, our smallest GFM is most ideal. So if we want least ideal, which is what we do, we want to go with the largest one, right? The smallest gas, smallest GFM, that's most ideal. So we're going to go with xenon. It's the most different from the ideal gas because it has the largest gram formula mass. So we'll be practicing with this with Regents questions in class.